Yo sé que aquí varios han sido miembros de examen de candidatura. Felipe va a presentar, bueno, es un ensayo de su candidatura y bueno, ya, adelante. Entonces ya, dale, Felipe.
Okay, so I will present my third semester exam for the thesis called Modeling Strongly Interacting Supernovae. So I'm Felipe Vargas, and my supervisor is Fabio De Colle. So I will show you a brief introduction with the thesis objectives and a brief motivation of the work. After that, I will introduce you our methodology, which consists in coupling a hydrodynamic code with a radiation transfer code and a genetic algorithm. Then I will show you the current advance up to now with some results. And after that, I will present the future of this work. So the the thesis objectives are characterize with precision the structure of massive shells around uh, progenitors of supernovae. So uh, we intend to model the density profile as function of distance and determine the metallicity and chemical composition and ionization structure of the medium of the circumstellar medium of the supernovae. So the idea is to apply these methods and to determine the circumstellar median of the supernova 2014C and this supernova 2001 EM. Um, we are going to model the physics involved and calculate the ionization fraction using applying photoionization, considering cooling, and also the H alpha emission. So we will do all of that coupled with a genetic algorithm, which is going to compare observational data with the models. So a brief introduction of the work. So as all we know, stars before collapse have this kind of onion layer structure where you have the heaviest elements on the center, on the core, and the lightest elements on the outermost layers. So some of these stars are really unstable and like Wolf-Rayet or luminous blue variables. And for or a star might be in a binary system, and due to binary interaction or the instability of the progenitor, the star before the collapse of the supernova might lose the outermost layers. So you have the expanding gas of the star, and you can create a dense circumstellar medium. And so that's important because that changes the how do you see the supernova, because the classification system of supernova is mainly based on the spectrum. So you have two main types of supernova that are supernovae type 1 that doesn't present hydrogen lines on its spectra, and supernova type 2 that do present hydrogen lines on the spectra. So if the star loses the outermost layers of hydrogen, for instance, it will be seen as a type 1. Okay. So uh, but for that's for a normal supernova. So if the supernova lost the outermost layers of hydrogen, it will be seen as type 1. But after the eject of the supernova interacts with the circumstellar medium, you might start seeing hydrogen lines again. So that changes the classification of the supernova. So for instance, the strongly interacting supernova, like type 2N, they are supernova that have interaction with the circumstellar material. So you have more regions that are emitting. So a common supernova usually emits from this region 4, where is the freely expanding ejecta, which is emitting. But strongly interacting supernova also have the influence of this region 1, which is the neutral material that might absorb some of the radiation. And you have this region 2 and 3 that are regions of interaction. So you have the foretrack of the ejecta interacting with a dense circumstellar medium, and that's going to emit usually in radio or X-ray, while a common supernova usually emits most of the bolometric radiation on optical. So we are going to study this strongly interacting supernova by using this methodology, which is we are going to couple 3 main codes. So there is the hydrodynamic code, which is going to make the simulation of the supernova. So the code was created by my supervisor, and the code is called Mescal. And we couple this code with a simple radiation transfer code and with a genetic algorithm. So in red we have the parts of the code that are not ready yet, and in black we have the parts that have already been done. So the hydrodynamic code usually solves the the conservation equations that for mass, momentum, and energy. And we are also going to consider cooling. So this work have on this paper there are tables of cooling, and we are going to put that and consider that on the hydrodynamic simulations. As post-processing for each frame of the simulation, we are going to compute the radiation transfer. So we take this last equation, which is the solution of the analytical solution for the radiation transfer equation, and we compute that in each cell of the simulation projected on the line of sight of the observer. So up to now we have implemented Bremsstrahlung emission, and we are going to consider other effects, but we put the emissivity and the absorption coefficients for Bremsstrahlung, for instance. We compute that on the source function here, and you can add other effects on this area. As a future work, we are also going to consider photoionization. And so here the dotted lines are observational data, and here the author have a subroutine with fitted equation that can model pretty well the observational data with this black line here, with this black continuous line here. And we are going to use their equations also for recombination. So they have the recombination rates compared to observational data as well. and it fits pretty well. And we are going to use that and couple and consider that in the radiation transfer code. Also, we are going to, as a future work, consider H-alpha emission. So we have already the subroutine here that we are going to couple with the radiation transfer code. So we are going to consider the contribution for collisional excitation and radiative recombination, and have the H-alpha emission as function of the densities, neutron and total, and the temperature of the gas. So the last part of this couple codes is the genetic algorithm. So the genetic algorithm is a technique based on natural selection. So it finds solutions to difficult problems which otherwise would be impossible to solve or take a lot of time. So the genetic algorithm is an optimization method, and basically we have an initial population of solutions for the problem that we estimate, and we start to create mutations on this initial population. And so that changes the initial conditions of the problem. Then we use we use these initial conditions created by the genetic algorithm on the hydrodynamic code and apply the radiation transfer code as post-processing in the results of the simulation. Then we calculate a fitness function to see how well fitted are these populations of solutions. And we calculate how good they are comparing with observational data. After that, we select a few of the best solutions. So we select the survival, then we do all over again, and then after some interactions, the solutions start to convert to a solution which is closer to the observational data. And we have the stop criteria that might be uh, a value, for instance, a low chi-square value or a certain number of interactions. So after we reach that, we stop and we have the optimized solution for the problem. So I will show you later an applied work that might provide you a better example of how does that work. So current advances up to now in my third semester, I have already a paper which is ready. So the name of the paper is Survival of the Fittest, Numerical Modeling of the Supernova 2014C. And so we applied this methodology without the parts of the radiation transfer we don't have yet, but we applied this methodology and we found a profile density for the supernova and the metallicity of the circumstellar material. So the motivation of that was our work of Margotti in 2017, where they study they have the detection of X-ray emission, and which is well fit to bremsstrahlung emission, to free emission. So they have a simple model of a density profile, and they show as well that the temperature of the supernova increases with time, and also that there is this column density here, which decreases with time. And they also show that the X-ray emission increases with time, which is not normal. So For a normal supernova, which doesn't have interaction, strong interaction with the circumstellar medium, the X-ray luminosity should fall with time, not increase. So this interaction is a source of emission. And so to try to model the supernova with strong interaction, we use the Hager profile, and we use this initial profile density for the star and make first simulation of the propagation of the shockwave inside the star for the supernova. So here we have a video of the numerical density as function of radius of the propagation of the shockwave. And we take this last frame when the shockwave leaves the star. We take this last frame as an initial condition for the simulation outside the star. So we have a separate simulation of the propagation of the shock outside the star, where we compute and we simulate the interaction with the circumstellar material. So as a first approach, we took the density profile of Margutti and we applied it in the simulation. And so the shockwave continues moving for outside the star and interacts with this region. So we use the radiation transfer code to compute the radiation, and we try to before applying the genetic algorithm, we tried around 2,000 simulations with a grid of parameters where we changed mass, radius, and the thickness of this outer shell of the star, and we tried that and we compared with observational data, but we didn't have a really good fit for the data in many different days, because they have many different days of observation. So here we have an example of 1 day of observation and some of the simulations we did before. So we decided to use the genetic algorithm to explore bigger sample of parameters, and the result was we had a much more complex dense profile, which is here. So we had this shell outside the progenitor, and here is the shockwave of the supernova in many different days. And here we have the temperature and how the velocity is changing. So we could compute the shock position. We could track the shock position in many different times, and also the shock velocity. So as a result, we were able to determine the density profile of this outer shell for many days of before and during interaction with the supernova. So here we have the density profile before interaction, and we have the density profile during interaction with the supernova. So that's the density profile here we determined. And here we have the comparison between the emission, the free emission with observational data for many different days. So we have the days of interaction and the observational data. The solid line is half metallicity, and the dotted line is solar metallicity. So the solid line is half of solar metallicity, and this gray area is from iron peak we didn't consider with the fitness function. So That's why it's not modeled here, because it wasn't from free emission. And we could see here that the half solar metallicity fits much better to the data than the solar metallicity. And so the density profile, this complex density profile had a much better fit to the emission than other simple profiles we had before. So here we have a zoom on the density profile of the shell outside the progenitor of the supernova. And we can see here that if we have this r to the minus 2 behavior, which would be corresponding to a steady wind. And here we have a different behavior for the density, which is different from a steady, what you would expect from a steady wind. So it might be an outburst or a quick change on the velocity of the wind. And so the conclusions of the paper are that the r to the minus 3 behavior indicates that it was not a steady wind. The shell has a complex density profile, and this outer shell has half of solar metallicity. Also, you are able to apply this technique for the first time in the field, which is called coupling the genetic algorithm, radiation transfer, and hydrodynamic simulation all together. So it was the first time it was applied on the area, and we have created a technique very fast to solve this difficult problem, which is modeling strongly interacting supernova. And we could apply it to more observational data for the same supernova, 2014C, or other transients that have a similar behavior. So up to now, I have been able to keep up with the schedule, and I have finished my first paper on the supernova 2014C. In the future, we intend to do another paper considering those other effects for the radiation transfer codes. So we will have a more precise density profile and also consider a more precise metallicity. And we also intend to apply that to the supernova 2001 EN and to other supernova 2N, because supernova 2N are interacting supernova. So I have been able to finish the genetic algorithm, and now we are going to work on the new radiation transfer considerations. And after that, I'm going to write the thesis and finish. So as a future work, we also intend to optimize the search of parameters for the genetic algorithm. We want to add the Bayesian inference, so we have very smarter choices for the genetic algorithm. And before we consider at electron temperature and ion temperature equal. In the future, we intend to consider them different. And also, I want to add cooling, photoionization, and H-alpha lines. We have already a synchrotron code that we are going to couple with the radiation transfer. We want to calculate the dynamics of the outbursts. So we want to study the origin of the shell to see how the shell was formed using this method. And so we are going to apply our methodology to see the possible initial conditions that might generate this outer shell. So future applications, as I said in the schedule, are going to be the supernova 2014C with all radiation transfer parts that are not included. So in that way, we are going to increase the accuracy of the density profile and have a more precise metallicity and chemical composition. Also, we will do apply this methodology in the Supernova 2001 EM to calculate the same. And if we have time, we are going to apply that to the supernovas 2N, or supernova with strongly interaction with the circumstellar medium. So my references are bad. Thank you.
Perfect time, Felipe. Then I would prefer that the questions would be in English because Felipe is going to present in that language. Then first, I don't know, someone want to participate? Questions, comments, suggestions? Please, Antonio.
Okay. Hi, Felipe.
Hi.
Uh, just a tip, right? In some of your plots, you have some labels in Spanish and say some labels in English. Try to be homogeneous in the labels, yes?
Mm-hmm. Okay.
In the language. Also, I would like to try if you can explain me the slide 12 because you mentioned the cooling, but you have a one slide for the cooling, but you say uh, a little bit about the cooling. Why is important the cooling on your work, or
So
what?
so
Yes,
they on this work they have tables, cooling tables. So the cooling will be important to consider the loss of energy on the hydrodynamics. So we are not considering that right now, and we are going to consider that in the future.
but why you have one slide for this topic, the cooling, and you don't going to work in this feature in your actual simulation?
But no, but I will
Why not
consider that.
put?
I put that in the future, that I will consider cooling. I put
Okay,
here.
okay, no, all right. Also, I want to know if you can explain me more about the role of the algorithm, genetic algorithm in your work, because I don't understand at all why it's so important.
Because
Or,
so
or
for instance, here in the paper, we had as first approach, we tried to create a grid of parameters, and we tried to fit the data. So that didn't work. So the thing is, the genetic algorithm changes randomly the parameters, and we weren't able to model the hydrodynamics before. So it changes randomly the initial population of parameters, and uses the idea of natural selection to choose the best for like, for example, if you had a population of animals, so they choose the best ones that fit the environment. So here we are going to choose the best ones that fit the data. And so
but
they changed randomly the initial conditions of the simulation, and we are after many interactions, we keep taking the best ones that better fit the data, and we use that as a new initial population, and we change that, and after many interactions we have a much more complex fit for the data.
but why not use
No.
for example Monte Carlo process or something like that? Because I think you are killing flies with bazookas.
But
It's only to feed these data points. I don't know. I mean, I don't know.
But why? How would they use Monte Carlo
I don't know.
here? Like we change randomly the initial.
Because you Monte Carlo acts like that, no? Choose random parameters.
Mhm. Yeah,
And
yeah,
if not, and you want to choose random parameters to fit the previous data, no?
yeah. We choose. We generate random parameters and choose the
Mhm.
best one of between them. So that's a genetic algorithm. It's not very complicated. So you just change these initial conditions, see if it fits the data, and take the best one of them and do this interaction all over again. So it's
Okay.
it's very simple. It's not like difficult. Maybe my I didn't explain that well, but it's a very simple algorithm.
Okay. Alan, please.
Okay. I would suggest that when you leave your camera on when you're giving the presentation
Okay. Yeah.
and when you're answering questions. I think I mean, it's good that everybody else leaves them off, but it's helpful to make that contact. Okay, so I have a bunch of questions. Right. So if I understand correctly, you're using the genetic algorithm to find the parameters to fit a set of data. The way you presented it left me quite confused because you talked about using it as the genetic algorithm to select the best solutions to data. And, normally I think we think about, you've got a set of parameters and then from those parameters you have one solution. So I would suggest rephrasing the presentation in terms of not solutions, but either parameters or models.
Okay.
The genetic algorithm is optimizing the parameters or selecting the best model.
Okay, thank you.
Second, to continue Antonio's doubts. So how many parameters do you have in a typical model?
This one is around 30.
30. Okay, so I think it's worth saying.
What?
Sorry?
No, I didn't say anything.
Antonio,
Okay, so 30. So okay, so I think it's worth saying that the reason you're using this and not a more conventional downhill simplex, Marquardt, chi-squared minimization algorithm is because you have so many parameters. And multi-parameter optimization is a difficult problem regardless. Okay?
Yeah.
Otherwise it seems like you're just doing something trendy to be trendy. But no, you're doing something trendy because this is the right way to solve this problem. So you need to say why the other solutions don't work. Okay?
Okay, thank you.
I have more questions, but let me cede to other people.
Okay. Thank you.
Enrique, please.
Thank you. Hi, Felipe.
Hi.
So I was wondering if I understood correctly, you have an interstellar medium with a one-dimensional profile. Is that correct?
Yeah.
So how do you think it would have, if you had, you mentioned that something that could produce this would be winds or it could be a binary. I could also imagine magnetic fields interference. So if you had, for example, material which is mostly along the equatorial plane, then the profile is very different And radiation would be very different in different direction as well. So you would need probably to simulate something more complex. How do you think that will affect your results?
Okay. To answer that, first I will tell you the idea is in the future we consider two-dimensional simulations, but the problem right now is that we have we don't have smart choices for the genetic algorithm, so we have to do a lot of simulations. So the problem to do more dimensional problems, to solve more dimensional problem, is that the genetic algorithm is completely random right now. So many times it chooses initial population that's completely wrong. So that's why we're going to introduce Bayesian inference on the choice of parameters. So it won't be that random. So if for this first problem it was a good approach, but for problems that don't have spherical symmetry, for instance in a binary system, as you said, we might have to choose we have to consider two dimensions. So but I'm not sure how that would change the work, would change the profile. Like you would have a density profile that doesn't have spherical symmetry, and you would have a different emission in different directions. But I'm not sure how could I answer you this question without making the simulations, because all the model is based on these simulations. So I think that the answer would be very, very complex, you know. So
right.
Yeah, but we intend to consider that in the future.
Okay. All right. Okay, thank you.
Okay.
Diego, please.
Yeah, so I'm gonna sort of follow Enrique's concern. So what wasn't clear for me is multi-D is within your program for the rest of the semesters or not?
What? Put more dimensions, you mean?
Yeah,
we intend to as I said here in future work, we intend to add Bayesian inference, so we can do less simulations, and we can because up to now we have been using spherical symmetry, and we could use a high resolution for the simulations, and it didn't take that long. But for two dimensions, if you want to use a high resolution, we can't do that so many simulations, because it would take too much computational time. So we would have to make smarter choices for the initial conditions of the genetic algorithm. So if we could use Bayesian inference to choose better the initial population of we could reduce the number of the interactions of the genetic algorithm, and then we would have time to do that in 2D, for instance.
Okay, sorry. So when you say add Bayesian inference, that would make it faster in 1D, and so 2D may be approachable in your.
Yeah.
Okay,
yeah.
That wasn't clear.
Okay. Sorry.
Okay.
Yeah.
Then another recommendation I have is in the methodology that you put for your genetic algorithm. It's not always like for us that do not understand the genetic algorithm. Maybe instead of this, or apart from this, you can put like a methodology for dummies and just like put pictures. And so I will do this, and then I will do this, and then I do this, like to help the viewer understand with maybe like a fast, super easy example of the steps that you take.
Mm-hmm.
And you can add this, or maybe you can take this figure away, just so that the people that are seeing this understand it.
Okay. Okay.
Well, Rosa says that she loves the flux diagram. So apart from the flux diagram, maybe you can put an example, and in the flux diagram say, okay, so I'm here, and then I do this, and you continue in the flux diagram.
Okay.
Just help the audience a bit more in this figure.
Mm-hmm. Okay.
Then I have really fast, in your future papers,
mm-hmm.
you never really explain why you choose those specific supernovae.
Okay. Yeah.
So are you married?
I choose them because they have a lot to use optimization methods. You need a lot of data. So these supernova have a lot of data. That's why. That's why we chose them.
Okay. So maybe just mention that these have really good data, and that maybe the one of the 6th semesters, some other supernova comes ahead, and you use the other. Or are you married to these 3 future supernovae?
No, it's because of the amount of data. You need a lot of data to use optimization methods. Mm-hmm.
Okay. Well, I would maybe leave it clearer that why these 3 for the future.
Okay.
Okay. And then the last one, I swear, is can you explain how you can have a wind that goes as 1 over
Diego, estamos tomando rondas. Come on.
Okay,
¿No aprendiste
take...
compartir tus juguetes como niño? Okay.
I'll wait for round 2.
Okay.
Alejandro, please.
Yeah, thank you. Hi, Felipe. Well, Enrique and Diego already asked you about the 2-dimensional simulations. I just want to ask, what priors are you using for the estimation of the initial parameters for the initiation of the genetic algorithm? Are you considering some observational parameters or some usual fitting parameters, or basically you're just randomly choosing?
It's random.
It's randomly? Okay. Have you considered looking for any some good prior that tells you which parameter is the best one?
Yeah. For instance, as I put here, we could use the simple models. This one, for instance, we could use this one. But the idea is when we start using Bayesian inference, is have a smart choice of priors before for each model, so for each supernova it might be different.
Okay.
If you analyze that and use some models, theoretical models that have already been made, we could use that so the solution appears faster. So yeah.
Okay. One last question. The article that you presented is already published, or
no? It will be submitted. We are only waiting that another group that is working with us, because they are the observationals. So we are waiting that they publish the observations, so we publish the theoretical model. Yeah.
Okay. Thank you.
Okay. First, Alan, I just want to say congratulations, because I think that it's very important that you have now read a paper. Then I think that you don't have any problems to pass the exam. Yes, I think that you are doing a very good job in your PhD. And then I have to leave, but the seminar is in hands of Leo. Then Leo.
Okay, thank you, Rosa.
It's all yours. And please, Alan.
Okay. Right. So at this moment, if I understand correctly, your code is pure hydrodynamics. And you're going to add photoionization, cooling, radiation transfer, and H-alpha, collisional excitation, and radiative recall. You seem to present it that you'll do this little bit by little bit. Okay, and that confused me because, for example, it's difficult for me to understand how you do a code with radiation transfer if you don't, for example, have photoionization, because the photoionization, determines the ionization state of the material, and that determines its opacity, which is very important for radiation transfer. So are you really going to do this, all at once, or are you going to do it part by part? And if you're going to do it part by part, can you explain to me what part first, second, third, and why you think they're independent?
Okay, so the idea is that the photoionization, recombination, cooling, and everything else will be put together. In the first simulation we had, we considered that the medium was completely ionized. So according to the observations, it was a good approximation. But that might not be true in other cases. So we could do that on this first supernova without problem. But in the future, we intend to put that all together. And I think that will be done quite fast because these works are presented. They have the tables and they have the fit equations. And we could add that. So in the first simulation, it was an approximation to consider the opacity. But from now on, we want to consider everything together.
Okay, that wasn't clear to me. Okay, thank you.
Thank you.
Okay, now it's the turn of Diego and then Fabio.
You first, Fabio. I asked already.
Yeah, so I think the important part is that, well, congratulations, because it's much better than the previous version. No?
Okay.
The important part is how clear was to everybody else the explanation about the genetic algorithm. Did you understand? I mean, the question is for everybody. Did you understand how the genetic algorithm is used or not? Because my impression is that it was not very clear, no? But I don't know if it just if that was my impression or if it's so. Is it clear?
It took a lot of effort to understand.
Sorry?
I understood, but I had to work to understand it. The presentation wasn't clear.
Okay, so I think this slide is important to. I mean, it's much, as Diego said, no, it will be much better if you put an example of how this is done in practice, no. And something, well, when you say that to use optimization methods, you need a lot of data, really, no. If you do a fit of 3 points with a line, that's optimization.
Yeah, no? But we'll be wrong. Like
wrong 3 points, you have a big error.
Yeah.
It's more on. You need to see it more from the observational point of view. No, if you have a lot of data, you have much more information about the supernovae. the particular supernova that you are studying. So it's much more interesting to study a supernova in which you have a lot of data available. No? So that's why the supernova 2014 is so good, because they observed it for 10 epochs.
Mm-hmm.
It was the first supernova studied in so many epochs. That's why it's particularly interesting. No? And yeah, these are my comments now, and we will talk later about other things.
Okay.
Felipe, thanks.
Thank you.
Okay. So I mean, not for the presentation, but just like, do you know then how many groups you are competing with?
I've never seen some. I mean, I have seen people modeling supernova, but this is the first time this method is applied. So, like the work is novelty, you know.
Okay. Yeah, that's my point. Just so you're like the novel, the first person that's doing this as a novelty, and no one is doing it because it's boring. That's my point. Just like be able to sell it that you are visionario, you know, like that the study is going to be groundbreaking.
Okay, thank you.
Trailblazing, this Enrique. Okay, and then the question I wanted to ask is physics. How can you have a wind that goes as 1/r⁴?
It's not a wind. That's the point. That doesn't behave like a wind. It's an outburst or like something, because as we didn't study the origin of the shell, we can't say for sure what happened. But for instance, you might have a binary system that stripped away the outermost layer of the progenitor, or you had a Wolf-Rayet star that had an outburst, or some like massive stars have instabilities before collapse, and they might lose their outermost layers. So this indicates that the behavior is not from a wind or a
but
steady
it can be a wind. Exacto. It's not a steady wind, but it can be a wind in which the m dot varies.
Yeah, you can have. So that's why I said steady wind here. And so we know that's not a steady wind, but it might be a wind, but we didn't study the origin of the shell. Yeah.
Okay. That's it for me.
Okay, thank you.
Alan, do you have another question?
Hey, it helps if you turn your microphone on. All right. Getting back to the genetic algorithm and Fabio's comment, that he worried that people didn't understand it. I don't think it's necessary to understand it in the sense of what it does. I think it's necessary to explain more clearly what problem it is solving. So if I were giving your presentation, I would say we're using a genetic algorithm to solve a multi-dimensional minimization problem. Punto. And then I have a slide prepared at the end, maybe this one, maybe the examples that Diego asked for, that explains it in more detail.
Okay.
But, it's really just a tool, okay? Like the computers are a tool, okay? You don't have a slide on the computers. They're very interesting, but they're a detail. This flowchart for me, I don't think it helps you present. I think it's much more important to say what problem you're solving. Diego's raised his hand, so maybe he has a comment on this. So, Diego, I'll see to you.
Yo no te comprendo, Diego. Como que está muy mal tu audio.
Alan, can you turn off your mic?
Okay, Diego.
Yeah, me now?
Kind of. I think it's your internet or mine. I don't know.
No, I think it's Diego's internet. Too.
Yeah, your internet's very bad. I think.
Okay, Diego put in the chat that he agrees with me.
Okay.
I'm going to take a screenshot of that. Okay. Okay, I have another question. Is there anybody else? Alejandro, yes, go.
Yes, my only question was, I want to ask you, is this genetic algorithm similar to the one that people use like for making Mario Bros runs the level by himself or something like that? Or is more complicated or is less complicated?
No, it's similar.
It's similar. Okay, because the basics on that, maybe on explaining how the algorithm works, I agree with Alan. Maybe it's not quite useful. Maybe it can be quite a technique, and maybe try to explain the behavior of the algorithm, not the physics and all that, just the behavior. Like if you are talking to a 5-year-old boy, like trying to make him entertaining or something like that, and just to say how genetic algorithm work, but put a lot of effort on which parameters are you using, and the thing that is a new thing in hydro radiation physics and computation. And yeah, maybe the explaining the algorithm, how does it works, maybe is not that important for the presentation, but have a backslide in case someone asks you technically. I don't know who is the synodom. I don't know who are they, but maybe you can think, maybe I think I saw Raga. No, maybe Raga wants to know. I don't know. But yeah, maybe have a backslide and focus more on the parameters and on the novelty of using this.
Okay, thank you.
Okay, it's the turn of Fabio and then Alan again, please.
Yeah, just a suggestion. So I think in the paper we explained very well the context relative to the Bayesian. Right, Alan? Bayesian.
Yes, more like Bayesian.
To the Bayesian.
The E es un poquito más largo con E en español, pero Bayesian.
Okay.
Bayesian.
Okay.
So just to mention it briefly. So if you can go to the slide where you have the grid of simulations. Because this also answers the question by Diego on what is the importance of this, of using this strategy instead of using others, and why no other people are working on this. Because it's not really simple, no? I mean, okay, so first of all, Felipe has done 2,000 simulations changing mass, radius, and size of the shell. And the results were kind of bad because there was not a good fit with the data. That implies our interpretation was that the shell is not uniform. No? I mean, is not constant, the density profile. So what is the density profile? Felipe is using different points in the density profile as parameters of the genetic algorithm. And what he is doing substantially is, okay, he's putting one simulation with a density profile. The genetic algorithm changes that density profile randomly. So imagine that you have one simulation. You produce 100 new simulations, changing the density profile in each of these 100 simulations. You run these 100 simulations, and you select the best 10. I mean, the 10 simulation in which that density profile interacting with the supernova ejecta produces the best fit with the observation. You select the 10 best density profiles and you reproduce the same method. So you change each one of these 10 density profiles and so on. The number of parameters is so large, so it's around 10 parameters, that if you want to explore 10 values for each one of these 10 parameters, you would need 10 to 10 simulations, no? A grid of 10 to 10 simulations. Instead, using this algorithm, you can do a few thousand of simulation, which is still a huge number. So it's a multi-D, it's a very complicated not to do it because it's a huge number of simulations, and converging to the correct one in a much quicker way. So the point is that doing this, coupling the hydro with the radiation transfer computed as post-processing with the genetic algorithm, which automatically changes the density profile, and running again simulations. You run a simulation, you change the density. You run 100 simulations, you change the density profile. You run another 100 set of simulations, you change the density profile, and so on. You do that 50 times, and at the end you converge to the correct result. This is something really challenging to implement. It's not easy, no? That's the complexity, why people has not done something like this. The advantage of that is that usually people do grids of simulations, and they compare the best, they compute the best simulation in this grid, and the number of parameters that can be explored in a grid of simulation is limited, while using this kind of method, you can explore a much larger number of parameters, and you can use the densities at different radii as parameters of your simulation, no? So I think you should try to explain this, no? Because I think this was not clear. I mean, it's not really the explanation of the genetic algorithm, but I mean, all the context, no? The method in general, no?
Mm-hmm.
That's all. That was my comment.
Okay, thank you.
Alan, please.
Okay. Well, to respond to Fabio, I don't think the right comparison is between a genetic algorithm on one hand and an exhaustive dense grid on the other, because obviously a dense grid is very inefficient. I think the right comparison is to something like downhill simplex.
Mm-hmm.
I mean, when I'm fitting the aberrations of a telescope, I'll take an image out of focus, and then I'll fit that image with a model of the out of focus image with all of the aberrations in the system. And I regularly have 20, 30, 40 parameters. And I use downhill simplex. I could also use a genetic algorithm, but downhill simplex is simple and works. So I think that's the comparison you have to make.
Yeah.
There may be in this particular application a specific advantage of the genetic algorithm. If there is, say it. Yeah.
Do you want to Felipe? Do you want to comment? Why the
Alan, we have returned from your microphone. Could you? What did you say, Fabio?
If you wanted to comment, or if you wanted a comment.
No, you can comment.
Yeah, that's a good point, Alan.
Yeah, it's a good point.
The paper we specified, that we really choose a genetic algorithm, but I mean, the importance is not the particular optimization method used. The important is applying optimization methods directly to numerical simulations. So yeah, you are right. You can use genetic algorithm, or you can use other methods, and it's in principle you should get the same result, no?
Mm-hmm.
And probably the genetic algorithms are in general not so efficient. So probably if you use other methods, you will get the same result faster, no? That's why Felipe has this idea of implementing other methods which can obtain the same result faster. Yeah, the point is, and yeah, you should specify that in the presentation. The point is applying the hydro with optimization methods, not in particular genetic method, but in general optimization methods. Good point, Alan. Yes, thank you.
Okay, yeah, thank you.
So Alan, please, and then I think Alejandro, and then Edwin have a question.
Okay, my final question is a comment, actually. I think you did a fairly good job in the presentation of explaining what you're going to do. Okay, but I don't think you did a very good job of explaining why. Okay, I don't think you explained, and this came up in several people's comments. Why are you working in 1D or 2D or 3D? Why are you putting radiation transfer and all its effects in? Why did you select these supernova? Why are you using a genetic algorithm? I think it's worth, in every case, if you're going to do something, say, I'm doing this because, and then say why it's important in terms of getting good results.
Okay.
Okay.
Thank you.
My comment was on these optimization methods, maybe trying to also go into the question of Antonio, of Monte Carlo's approach. I think other thing, I don't know, I'm new in these kind of methods, and so I don't know, but yeah, there is no, as far as I know, there is no use of this kind of optimization methods with hydrodynamic codes. So maybe another application and another extent of your work that you can do is, since you already have an optimal fitting for your parameters, this kind of sinusoidal shape that you obtain and all the density profile and etc. Maybe taking this, you can also think of a some prior distribution of these parameters that may give you like an error estimation of your model compared with the simulations, maybe, I don't know. And for this, you can try some Monte Carlo simulation or Monte Carlo Markov chain simulation, etc. Maybe you can do that. It is a different prior from the initial parameters that you made, but maybe you can do that. And this is this may be like a distribution of all the possible, not the best one, but all the possible best one distributions that fit that experimental data. No? So maybe you can also extend in that way. I don't know if it's possible. Maybe the prior distribution that you have to think of is really complicated. I don't know. But if you also give an error estimation from your simulations in comparison with your data, I think that we are really great bunch, and it's not used to, well, people that use to make simulations, hydrodynamic simulations, never give estimations of the error of our simulations in that fashion. So it might be a really good point to make for your future articles, I think. Maybe, I don't know.
Yeah, the thing about the prior, I have to study more to see, because we have, like, it's the first density profile we have done for the supernova 2014C, and maybe, I don't know, maybe they have similar behavior in other supernova. And also, yeah, we have to optimize that, but I'm not sure how to calculate the error, because, I mean, we do the hydrodynamic simulation, calculate the emission, and then we compare the emission, but I'm not sure we have a way to calculate how wrong is the profile density.
Bootstrap?
Yeah, maybe Bootstrap. Yeah.
Mhm.
Yeah. So yeah, we could do that, but it would
Yeah.
take much more computational time, I think.
Maybe, yeah, maybe. I think so, but I think the simulations are quite fast. I think.
Yeah, for 1D, yeah.
Or I don't.
Yeah.
Okay. Yeah, for 1D. Yeah, so yeah, for 2D, it's likely not impossible, but it's not quite efficient.
Yeah. Mm-hmm.
Okay, so the question of Antonio is, so it is worthless try a Monte Carlo approach to the amount of parameter in principle? And then Fabio.
I'm not sure what would change, because I mean, we are doing we have to use an optimization method because we, as Alan said, we have a lot of parameters, and we it's the best way to solve that is using an optimization method. I'm not sure how I would apply a Monte Carlo in that way, and like because I mean we have random initial parameters, so that's pretty similar to what the Monte Carlo method would do, but I'm not sure how we would apply Monte Carlo method to these initial parameters. I think it would be I don't know. Yeah.
The genetic algorithm uses Monte Carlo.
Yeah, it's like
so
you are changing the initial parameters as a Monte Carlo code would do. So yeah, I'm not sure it would change anything. Yeah,
it's because that's the philosophy behind the Monte Carlo methods, like using random set of numbers.
Yeah, we already do that, but we have generations and we choose the best between them, and we repeat that many times. So it's the genetic algorithm is kind of repeating Monte Carlo many times.
Yeah. Maybe the thing can improve is Monte Carlo Markov chain, which which basically looks for the best path to follow to get to the optimization parameters, optimal parameters, basically.
Yeah,
I don't know if maybe the genetic algorithm is making some of kind of Markov chains.
Yeah,
sort of stuff. I don't know.
It's not doing, because that's the inspiration to use Bayesian inference is from Monte Carlo Markov chain. That's the idea. So in Monte Carlo Markov chain, you use Bayesian inference to choose the path. So the choices are not that random, and so you can have fewer interactions. The idea is the same. We want to use Bayesian inference to choose the best path, and so that the genetic algorithm is not that random. Yeah.
Yeah. Yeah, that might improve it really well.
So if anyone have another question, please do it. If no, let's thanks to Felipe, and let's go to it.
Thank you very much. Thank you very much.
Thank you,
Thanks for the presentation, Felipe.
Yeah.
Good luck.
Te va a ir muy bien. Te va a ir muy bien, vas a ver.
Muchas gracias.
Con este artículo que ya casi sale, vas a ver que sí.
Está bien, gracias.
Felipe.
Sí.
Nada más era de eso que te decía, que por ejemplo en este slide tienes datos.
Ajá.
La palabra datos, que como que las trates de homogeneizar.
Ah, sí, que poner todo en inglés, sí. Es que no había visto. Sí, gracias. Ajá.
Sí. Bueno, muchas gracias, Felipe. Estuvo muy bonita, suerte.
Muchas gracias.
Ahí nos avisas cómo te va.
Sí, está bien. Gracias.
Saludos, cuídense.
Ajá.
Bye.
Adiós.
Chao.
Chao.